So we are headed into Chapter 8, and that is Electron Configuration and Periodicity. Based on what we've learned about orbitals and where those electrons live, and remember that it's going to be that three-dimensional shape that tells us where the electrons are most probable to be. And again, thinking further ahead about chemical bonding, these orbitals have to overlap to form chemical bonds, and they have to be similar in energy to overlap and have the right shape to overlap effectively. And what we can start to do is relate that to different trends that we see on the periodic table. So we're going to further define where those electrons are and then relate it to different characteristics on the periodic table. So this is just a review of the quantum numbers. We want to make sure we know how to use these. And we have 4 different quantum numbers. Let's go back. So something we want to remember is that every single electron in an atom is going to have its own unique set of 4 quantum numbers. So we have the principal quantum number telling us something about the size. The angular momentum tells us what type of orbital, if it's S, P, D, or F. The magnetic quantum number is going to tell us how many orbitals we have and something about its orientation in 3D space. And the part that we're adding in is the spin, so the direction of the electron spin, either +1/2 or -1/2. And the initial experiment done to show that we have that last quantum number is this one, where you have a source of hydrogen atoms and you channel it into one beam, and you basically run that through an external magnet. And what happens is that beam splits into 2 different paths. So you have one situation where the magnetic field that's generated by the electron is either going to be going in the same direction as the external magnetic field, and we call that +1/2 spin, or it can be going against the external magnetic field, and we call that -1/2. So we want to start to think about how the electrons occupy these orbitals. So we call this an electron configuration, and it basically tells us where those electrons live, and it goes in a certain order. So for example, if we look at the periodic table and relate this for fluorine, we have the 1s orbital. We always start at the top. We have 2 electrons there. If we go down to the next period, we have 2 electrons in the 2s orbital. And then we jump over to the P block, where if we stop at fluorine, we occupy or have 5 electrons there. An orbital diagram further shows those electrons in their spin. So it's going to show the direction of the arrow either pointing up for the +1/2 or down for the -1/2. So that's going to be the spin quantum number. And we want to look at the exclusion principle. So this tells us again that no 2 electrons have the same 4 quantum numbers. So that last one, spin, is going to make the difference between 2 electrons, even if they are in the same orbital. And then orbitals can have no more than 2 electrons. And again, they have to have opposite spin. So we want to initially look at a single electron. And I think we looked at this energy diagram in the last chapter, where as long as I have the same principal quantum number, the energy only depends on that principal quantum number. And this is true as long as I only have 1 electron. So notice that when I go up to the 2s and the 2p, those orbitals or their energy levels are degenerate, meaning that they're the same in energy. And same thing happens for the 3s, 3p, 3d. So as long as I only have 1 electron, it's only dependent on the principal quantum number. But as soon as we start to add in more electrons, this changes. So notice that I have 2s down here, and then 2p is a little bit higher in energy. So we want to start to think about why that's the case. And in this case, once I have more than 1 electron, the energy is not only going to depend on the principal quantum number, but it's also going to depend on the angular momentum. So something we want to start thinking about is how other electrons in the molecule affect what that one individual electron feels. And that's what happens with this different energy pattern that we see. right? And we can write in the principal quantum number and the angular momentum for each of these. So we want to explore those factors, why we have differences in energy even if they have the same principal quantum number. So we have a few different factors that affect this. And the first one is going to be the nuclear charge, or Z. Okay, and we'll talk about what that is. The second one is going to be shielding by other electrons. And the last one is going to be the orbital shape. We've already talked about this a little bit, that again, if we are closer to the nucleus, those electrons, or electron density, it's going to be more stable or lower in energy. So a higher nuclear charge increases the nucleus-electron interactions and lowers the sublevel energy. In other words, it just means that those electrons are held in closer to the nucleus. So that's always going to be more stable. So that means you have a high effective nuclear charge. That particular electron feels that positive pull from the nucleus really well. So we want to think about why, and we've talked about this a little bit, but just think about charge. We know that the nucleus has protons and neutrons, so overall positive charge. So those electrons want to be pulled in closer. If they feel a higher effective nuclear charge or pull from the nucleus, that is going to be stable or lower in energy. This next factor is going to be shielding by other electrons. So even though the electrons feel that pull from the protons in the nucleus, if you have other electrons in between, those can kind of shield or block what that electron feels, or block some of that pull. So something else we want to think about is shielding by other electrons and how it reduces the overall nuclear charge. So the nuclear charge, or the pull from the nucleus that the electron actually feels, is called an effective nuclear charge, or ZF. So this effective nuclear charge of an electron is going to be what that electron actually experiences again. Okay. For orbital shaped, we already talked about this a little bit. If we think about the shape of a 2s orbital versus a 2p, the 2s orbital is going to be held a lot closer to the nucleus, which means it feels that pull from the protons a lot more and is going to be more stable or lower in energy. So its Z effective would be greater for that particular orbital. Okay, so let's look at a few different cases. The first case, if we're looking at the effective nuclear charge, in this case we're going to have the same number of electrons. So we have hydrogen, we have helium with a plus charge, and we have lithium with a 2+ charge. All of them have the same number of electrons, but they have a different number of protons. So if we think about it, going from hydrogen to helium plus to lithium 2+, lithium 2+ has the greatest number of protons, meaning that that pull from the nucleus is going to be a lot stronger, since they all have the same number of electrons. The number of protons we have is higher, it's pulling a lot more, or holding those electrons, or that one electron, closer to the nucleus. So it has a higher effective nuclear charge. Or we could say that since this electron is being pulled so close to the nucleus, it's going to be a lot harder to remove that electron. Okay, make sure I said electron for this one. All right, so again, the greater nuclear charge is going to lower that sublevel energy. Okay, greater effective nuclear charge is going to be more stable or lower in energy according to Coulomb's law. So again, it's going to take a lot more energy to remove a 1s electron from helium with a plus charge than hydrogen. And again, that's because helium plus has a greater effective nuclear charge. It's being held more tightly by the nucleus. Let's also look at shielding and orbital energy. So we can look at two different cases. The first is where we have electrons that are in the same energy level, or the same level. So in terms of shielding, or basically blocking that pull from the nucleus, if those electrons are in the same energy level and right next door to each other, it doesn't have a great shielding effect. All right? So it's going to make it slightly easier to remove one of these electrons as opposed to just having the one electron out there, but it doesn't make a huge difference. Let's look at another case. So when electrons are in different levels, so let's look at this electron out here. Since we have these electrons in between, this electron in the nucleus, these are having a shielding effect. Basically, these two electrons are blocking what this electron out here feels in terms of pull from the nucleus. So it's actually a lot easier to remove this electron because we have these electrons kind of blocking the pull from the nucleus. Whereas if I don't have any electrons in between, it's going to be harder to remove this electron because it feels that full pull from the nucleus. So starting to think about the order of stability of the different orbitals, something we can look at is the radial probability distribution. So we can compare the 1s, which is really close to the nucleus, the 2p, and the 2s. And initially when you look at this, you see that there is this significant electron density for the 2p that's actually a lot closer to the nucleus than the 2s. So initially looking at this, I would think that the 2p would be lower in energy or more stable than the 2s. But if we look at the 2s, there is this region that actually gets very close to the nucleus, and it actually overlaps with or is able to penetrate closer to that region where we get a high probability of the 1s. So even though we have a lot of its probability kind of further away, because of this small region where it's able to go in very close to the nucleus, it actually makes the 2s sublevel more stable than the 2p. Okay, and then if we go ahead and put all of our orbitals together, in general, the s is going to be more stable than the p, more stable than the d, and then more stable than the f. Right? So if we put them all together, all of our energy levels, we can look at this. So we can say that our orbital overlap and shielding causes the orbital energies in the same shell or the same n level to not be degenerate or not be the same. So now we have to take into account what the other electrons are doing and how it's influencing that specific orbital. So if we look at n equals 4 and n equals 5, that effective shielding and orbital overlap becomes so important that the s orbital actually lies lower in energy than the d orbitals of the previous principal level. So that's why we have this kind of, at least not as predicted, energy level order. And then we can also say that the energy separation between one set of orbitals and the next becomes smaller beyond the 4s. And we can say at this point that the electrons are going to be so far away from the nucleus and so shielded that there's not going to be as great of a difference in those energy levels. So ordering can therefore vary quite a bit, and this causes variation in electron configuration of transition metals. So for those electron configurations, especially the lanthanides and actinides, they're not going to be as predictable. And here's an online resource that you can use to look at those if you like. So what we want to do is we want to compare the 3s and 3d orbitals for beryllium with a 3+ charge. So first thing we want to do is write the electron configuration. So if we have beryllium, so we know that its electron configuration on its own is going to be 1s2 and then 2s2. Okay. If we have beryllium now with a 3+ charge, we know that electrons are negatively charged, so we want to start removing electrons. We want to remove the outermost ones first, so we'll remove 2 of those, and then we'll remove 1 of these, so it's just 1s1. Okay. Since we only have 1 electron in beryllium 3+, and we said that if we have 1 electron, that makes the orbitals that have the same n number or n level the same. So that means that these two will be the same. because we only have one electron here. So why don't we do a similar thing here? We want to compare the energies of the 2p orbitals of lithium 2+ and beryllium 3+. So we already know that beryllium 3+ is just 1s1. And then for lithium, if we go ahead and write the electron configuration, we get 1s2 and 2s1. If we go ahead and take away 2 electrons because of the +2 charge, we get lithium 2+. We take away the outermost one first and then one here, so we get 1s1 as well. So we actually have the same electron configuration for both of them, so these will be the same in energy. Something else we want to explore is how we start to put those electrons in. So this is the Aufbau principle. And initially, if we are putting in our electrons, we can do something like this, where we go ahead and, for example, in our 2p, we fill both electrons in the same orbital first. Okay, but we want to think about that. And I like to think of it as being similar to when I get on the train or when I get on a plane. If you have the choice between an open aisle or sitting right next to someone, which one are you going to do? Maybe you're friendlier than I am, but I'm going to go for the open row. So we want to think of electrons as wanting to do the same thing. They're negatively charged, they repel each other, we want to do the same thing. So if we have electrons to fill in, and we have degenerate orbitals that are the same in energy, we want to singly fill them first, and then we can go back and fill them in paired up. And it's because we want to spread those electrons out as far as possible. So for Hund's rule, the most stable arrangement is the one with the greatest number of parallel spins. And then going back to the Aufbau principle, we want to make sure we start with the ones that are lowest in energy first and then fill up. So we want to think about what element is depicted above. So if we have 1s2, 2s2, 2p3, we have nitrogen. So here comes the order of orbitals or filling multi-electron atoms. So this is the order that we want to know. So here's the overall order, and you can follow this kind of slant to know the orders, but this is something that you have to commit to memory. Okay. So we have the complete electron configuration, where we have the principal quantum number, we have the angular momentum or type of orbital, and then we have the number of electrons in that orbital, or what we call a subshell. So here are some examples for hydrogen, helium, and lithium if we want to draw an orbital diagram. Okay, so if we start relating this to what we see on the periodic table, we have the S block, these first two groups. We have the P block over here. We have the D block, and then we have the F block. All right, so we're holding, we have one orbital or 2 electrons. For the S, we have 3 orbitals or 6 electrons for the P, and going straight across for the D, we have 5 orbitals or 10 electrons. For the F, we have 7 orbitals or 14 electrons. So we want to find the electron configuration of magnesium. So we can start with 1s2, 2s2, 2p6, and 3s2. So we're going to stop at magnesium. Or if we want to write it in a shorthand way, we can go to the noble gas that's right above it on the periodic table. So the last noble gas that comes before magnesium is neon. So this in brackets stands for everything before. So all of this portion is covered in this. And then from there we just have 3s2. So just pay attention to whether it says shorthand configuration or the full electron configuration. Next is, what are the possible quantum numbers for the last or outermost electrons in chlorine? So we want to see what period it's in. So n is equal to 3, which means our possible angular momentum numbers are 0 and 1, which correspond to an s orbital and a p orbital, which tells us we have a 3s orbital. And then for 3p, we have a px, a py, and a pz. And for each one of those, we have a spin of +1/2 or -1/2. We want to write the electron configuration for antimony and its diagram. So let's start with the electron configuration. Notice here that we go from 4s to 3d and then back to 4p. Or we can write it the shorthand way by looking at the noble gas that's directly above it in the periodic table, and then we can just tack on the rest here. Okay. So a few more things on valence electrons. So valence electrons are going to be the most important ones because those are going to be the outermost electrons. Those are the ones that are actually participating in chemical bonding. So those are going to be are basically electron glue that's holding bonds together. However, the group number in the periodic table always defines the number of valence electrons for any atom except for the F block elements. Okay. So the definition of valence and group number usually agree, but for transition metals, lanthanides, actinides, there are some differences, so we don't have to worry about those. We just want to go with the group number is always going to define the number of valence electrons. So we can look at group 1A, group 2A, and so on. Okay. I want to show you a few exceptions. So there are two that I want you to know, and chromium is one of them. This is how we expect to fill the electrons in for chromium. So we expect something that looks like this. But what happens is, since we have this almost filled or almost half-filled D shell or D subshell, we actually get something that looks like this. One of those electrons from the 4s actually gets transferred over to the 3d, and that, since we have what we call a half-filled shell, that's going to be lower in energy or more stable. So this is one that we want to know. And then let's say I have chromium with a charge on it. I want to remove this 4s first, and then I can start removing the 3d. Another one is of copper. So we have something similar where I'm filling in my electrons, and I get something like this where I almost have a filled d orbital, but not quite. So what it actually does is the same thing. One of these 4s electrons, or one of the electrons in the 4x, gets moved to the 3d, and we get something that looks like this, where we now have a filled d. Okay, so we have a filled d orbital. And again, that allows for some extra stability. It's going to be lower in energy. If I'm going in and I have copper that now has is an ion with a +1 or +2, then I'm going to start removing the 4s first, and then I can go back and remove the 3d. Okay, so again, since we are looking at ions, if we have a cation, we want to remove the number of electrons that's equal to the positive charge, and if we have an anion, we want to add in electrons that are equal to the charge. For transition metals, we're going to lose the ns, so that was the example where we lose, for example, the 4s electrons first, and then we start removing the d electrons. So here are some other examples. So here's one more example. We want to draw the orbital diagrams for iron and iron 3+. And if we compare, we see that for iron, we have the 4s filled, and then we have the 3d that's partially filled. And if we go from iron that's neutral to iron with a +3 charge, we want to make sure we remove the electrons in the 4s first, and then we can go back and remove another electron from the 3d. So always remove the ns first. So something else we can look at is magnetism. And what happens is when we have an atom that has unpaired electrons, and then we have some external magnetic field, those electrons are actually attracted to that external magnetic field. Whereas if we have an orbital where we have a fully filled subshell, those are actually going to be slightly repelled. So we call those substances that are attracted to an external magnetic field paramagnetic, again meaning that they have unpaired electrons. So these have applications in MRI, right? Lanthanides and actinides can actually have up to 7 unpaired electrons, so they can have really large magnetic moments. And some examples are neodymium and samarium, and because of that, they're small but really strong magnets that are used. Substances that are not attracted to an external magnetic field, meaning they have all paired electrons, are going to be called diamagnetic. Right? So we want to use orbital diagrams to figure out for both of these, zinc 2+, or titanium, we want to figure out if it's paramagnetic. Okay? So if we look at the electron configuration for zinc, we don't have, all of our electrons are paired, we have no unpaired electrons, so this is going to be diamagnetic. And then if we look at it for titanium, if we go back and write its electron or orbital diagram, we'll find that we do have unpaired electrons here, so it will be considered paramagnetic. So it can interact with some external magnetic field, where zinc 2+ cannot. So just a little bit of terminology here. We can have some different species that are isoelectronic, meaning that they have the same number of electrons, and therefore if we write out its electron configuration, they will be the same. So I just want to give you some examples of species that are isoelectronic. So here are a few examples of that. Okay, so here's one other example. If we look at sodium plus or aluminum 3+ or nitride, all of these are going to be isoelectronic with neon. So all of them have the same electron configuration. We want to think of what's isoelectronic with, we call H- hydride, and that's going to be helium. So they both are going to have 2 electrons. So now that leads us to one of my favorite topics, and that's periodic table trends. We can look at a few different things. So we can look at atomic size, which is going to be determined by how far the outermost electrons are from the nucleus. So essentially that N number, how many orbitals we have going out. So as we move across the periodic table, or a row to the right in the periodic table, the atomic size decreases. So we want to think about why this happens. And the reason is the electrons are filling the orbitals of same size, but the number of protons in the nucleus is increasing. So if we think about the number of protons, if we have a greater number of protons, that pull from the nucleus is greater, which means that it's going to be smaller overall. It's pulling that electron density in closer. So we can look at this. If we go straight across, they're getting smaller, and then as we go down, we're getting bigger. Okay. So again, as you go down a column or family, in the periodic table, the atomic size is now increasing, right? If we think about it, our principal quantum number is increasing. So each time we go down in the periodic table, we're adding in a new subshell. So it's getting larger and larger and larger. All right, so we can look at a pictorial view of that. So something else we can look at is ionic radius, if we're now talking about going from a metal to an ion. And if we think about it, when we take something like sodium and we lose that outermost valence electron, then we go to sodium plus and we lose that outermost level. So in this case, since we lose that outermost level, sodium plus, or the cation, is going to be smaller. So we can also look at that trend. On the other hand, if we're looking at ionic radius, it has the opposite trend, where then we would be adding in electrons, so we would expect that it would be larger. Okay, so that brings us to our next trend, and that's going to be ionization energy. So this is going to be the energy required to remove an electron from the outermost level in the gaseous state. So that's something we want to keep in mind. So if we think about it, as we move across the periodic table, we want to connect it to things that we already know. And a row to the right in the periodic table, ionization energy increases. So the fact that it increases means that it's going to be harder to remove that electron as we go across the periodic table. And we want to think about why. So if we go back to atomic size, as we're going across the periodic table, to the right, the atomic size is going to get smaller, right? So it means that those electrons, or those outermost electrons, are being held more tightly, which means you have to put more energy into it to remove that electron. So it makes sense that the ionization energy increases. But as we go down a column or a group, the ionization energy decreases. So let's think about that. We've learned for atomic size, as we go down the periodic table, that size is increasing, meaning that outermost electron is getting further and further away from the nucleus. So we expect that the outermost electron is more shielded, meaning it doesn't feel as strong of a pull from the nucleus, and it's a lot easier to remove. In other words, the ionization energy decreases, or it takes less energy to remove that electron. Okay, so again, we can relate it to things we already know. We can look at the atomic size and relate it that way. So we want to think about what is harder to remove. So the electron in this NS or the electron in the NP. So for this problem, we want to remember that these s electrons, or the ones in the s orbital, are going to be a lot closer to the nucleus, whereas the ones in the NP are going to be a little bit further away from the nucleus. So we expect these ones to be harder to remove, or it takes more energy to remove those versus the one in the p orbitals. Let's look at another problem where now we are comparing where we have 3 single electrons versus one set being paired. And in this case, this one is going to be harder to remove, or it's going to have a higher ionization energy. If we remove this one electron, then we get a half-filled shell. Okay? And we said that there's some special level of stability when we have a half-filled shell. So if we remove that one, that's what we get. Whereas if we remove this electron in the p orbital, we don't get that same level of stability. So something I want you to think about are, we have the general trends for ionization energy. If we look at ionization energy here, and we correlate it to some things we already know, we know that metals like to lose electrons more readily than nonmetals. So it makes sense that as we go across the periodic table, that the ionization energy in general is increasing. It's harder to remove that electron. But something that I want you to think about is we have these little bumps in the lines where we have a few that kind of stand out. So like boron or oxygen. I want you to take a moment, and you can pause the video, look at your periodic table, and try to rationalize why those ionization energies are a little bit lower, or why it's a little bit more favorable for those to lose an electron. And we'll talk about it more. So our next trend is electron affinity, and this is going to be the energy released when an electron is added to an atom. So I like to think of it as being the opposite of ionization energy. The one thing we want to keep in mind with electron affinity is that there are many exceptions. So we'll focus more on atomic size, and ionization energy and metallic character. Electron affinity has quite a few exceptions. So if we want to think about this, if we are adding in an electron, that is going to be more favorable for nonmetals. So you get a greater amount of energy that's released when you're adding an electron to a nonmetal versus a metal. So on this side, it doesn't want to gain that electron, so the energy released when you add in that electron is going to be a lot less. Or we could say it's going to be a lot less favorable. So something we can look at is, we can look at orbital diagrams again, and it's going to be a lot easier to add an electron to an s orbital than a p orbital. And if we think about it, if we're putting that electron in an s orbital, it's going to be held more closely to the nucleus, which is more favorable, than adding it into a p orbital, which is a little further away from the nucleus. It's going to be easier to add an electron to an empty orbital than one that already contains an electron. And for this, we can go back to thinking about electrons want to be spaced out as much as possible. So if it has the option of being in an empty orbital versus pairing up, it's going to be a lot easier for it to add to that empty orbital, or a lot more favorable. So another trend we can look at is metallic character, and we can relate it to things that we've already seen. So we know that metals like to lose electrons and nonmetals like to gain electrons. So as you move across a period or a row to the right, the metallic character is going to decrease. So things that we already know is, as we go to the right, ionization energy increases quite a bit because those elements are holding those electrons closer to the nucleus. They don't want to lose those electrons. So as ionization energy increases, electrons are less likely to be lost in a chemical reaction. As we move down a column or a family, the metallic character is going to increase. All right? And again, as we go down, we know that the ionization energy decreases, or it's a lot easier to lose that electron because those outermost electrons are a lot more shielded. The effective nuclear charge that it feels is less. So it's a lot easier to remove that electron. And one thing that we can look at, and I'll post a video of this again, is looking at alkali metals in their reaction with water. So in that reaction, we saw that as you go down the periodic table, it reacts a lot more violently. So it has more metallic character, it loses that electron more readily, and it's a lot more exothermic. It releases a lot more energy when that happens. So this is just a summary of all of the different trends that we have. So what I would do is relate them to one another. How does atomic radius relate to ionization energy? How does ionization energy relate to metallic character? And then how do electron affinity and ionization energy differ?